Hello friends, this is Parth Thakkar and today we are going to discuss about the black body radiation. In our previous lecture, we have discussed radiation mode of heat transfer and how radiation mode of heat transfer is different from the conduction and convection. Electromagnetic wave is responsible for the radiation mode of heat transfer. So let's start with our first slide. We know that a body whose temperature is about absolute zero emits electromagnetic wave in all the direction. Now the question is the amount of radiation energy emitted from a surface at a given wavelength. It depends on the different parameters, like it depends on the material of the body, surface condition of the body and the surface temperature. So at same temperature, different bodies may emit different amounts of energy of electromagnetic wave. So now it is very curious to know the maximum amount of radiation that can be emitted by a surface at a given temperature. So for that we need one reference to satisfy our curiosity, and that reference point to which actual body emission can be compared is known as the black body. This is idealized body, and the black body, it is our standard to which another radiative properties of the real surface may be compared. So a black body, it is a perfect emitter and absorber of radiation. It means a black body will absorb all the electromagnetic wave which incident on that body. It will emit electromagnetic wave of full range of spectrum of electromagnetic wave in all the directions. A black body, it is at a specified temperature and wavelength. No surface can emit more energy than a black body. Suppose we have two bodies, one is a black body and one is another real body. The temperature of both bodies are same, suppose 60 degrees. So at 60 degrees, the maximum amount of energy of electromagnetic wave emit by the black body as compared to the real body. So at a specified temperature and a wavelength, no surface can emit more energy than a black body. Black body absorb all the incident radiation regardless of wavelength and direction, as we have just discussed. It emits radiation energy uniformly in all the direction per unit area normal to the direction of the emission. As we can see from this figure, a black body is going to emit electromagnetic wave in all direction in uniform way. So a black body is a diffuser emitter. Diffuser emitter means it is independent of the direction. It emits same intensity of electromagnetic wave in all the directions. Now, so in sum up, black body is an idealized body, but we have to differentiate idealized black body with ordinary black surface, because a surface that absorb all the light, visible range of light, which is in a electromagnetic wave spectrum, the visible range is 0.4 to 0.76 micron. So 0.4 to 0.76 micron of electromagnetic wave is absorbed by some body. It will appear black to our eye because our eye has a limit of 0.4 to 0.76 micron of wavelength of electromagnetic wave. So the object which absorb all the electromagnetic wave of that particular narrow bandwidth range of 0.4 to 0.76 will appear black to our eye, but that doesn't mean that object is a black body. Suppose we cannot make judgment about the blackness of the surface on the basis of visual observation, because snow and white paint reflect light and thus appear white, because it will reflect all the visual range of wavelength of electromagnetic wave from 0.4 to 0.76 micron. But same snow and white paint absorb all the infrared radiation, all the infrared range of electromagnetic wave. So for the infrared range of spectrum, that snow and white paint is black, but for the visual range it will appear white for our eye. So we cannot make judgment about the blackness of a surface on the basis of our visual observation. So the question is, what is the real body that resemble closeness to the black body? A surface coated with a lamp black paint approaches idealized black body behavior. Another type of black body that closely resemble a black body is a large cavity with a small opening. As we can see here from this figure, a electromagnetic wave which comes in from this little opening will reflect number of times before escaping. So whenever it reflects number of times, a little portion of that electromagnetic wave will absorb. So before escaping from this opening, it lost almost every energy, every packets of photons within this cavity. So this cavity will closely behave like a black body. If we if this body is isothermal at temperature T. Now there are different laws related to the radiation. First one is the Stefan-Boltzmann law. We have just discussed. Let's sum up what we have learned up to this point. Every body whose temperature is about absolute zero emits electromagnetic wave. That electromagnetic wave contains packets of photon, or we can say that the energy. So every body whose temperature is about absolute zero emits electromagnetic wave of different wavelength, of different energy, because we know from the relation that the smaller the wavelength, higher the energy contains by the electromagnetic wave. So the question is, whose electromagnetic wave consider larger energy? So wavelength of the electromagnetic wave depends on the different parameter like temperature of the surface, surface conditions, as well as the material of the surface. At same temperature, if there are two bodies, one body emits more electromagnetic wave as compared to the another body. So for the comparison, we required one idealized condition, one idealized body, that is known as the black body. A black body is a perfect emitter as well as perfect absorber. It means it will absorb all the electromagnetic wave which incident on it, as well as at a particular temperature, a black body emits maximum amount of electromagnetic wave as compared to all other bodies. So it is a perfect emitter. Now we required one equation from which we can calculate the emissive power. Emissive power means electromagnetic wave emitted by a by a particular body per unit time per unit area. So experimentally, it is radiation energy emitted by black body per unit time and per unit surface area was determined by Joseph Stefan in 1879, which is given by EB. It is emissive power of the black body is directly proportional to temperature raised to 4. T is the temperature of the black body surface. So if we remove proportionality limit from this equation, we have to put one constant which is sigma, which is known as the Stefan-Boltzmann constant, whose value is 5.67 into 10 raised to minus 8 watt per meter square. Here T is the absolute temperature of the surface of the black body in a Kelvin, and EB is the black body emissive power. So from this equation, at particular temperature, we can easily find out emissive power of the black body. Now there is another law which is Planck's law, because at particular temperature a body emits a wide range of wavelength of electromagnetic wave, but in some cases we are only interested in a particular wavelength. Suppose if a light bulb emits electromagnetic wave at particular temperature, but we are more interested only in a particular visible range for the light bulb. We just want to know how much amount of electromagnetic wave is emitted by the light bulb whose wavelength is between 0.4 to the 0.76 micron, because this is the only range which is visible by the human eye. We are not interested in other wavelength than 4.4 to the 0.76 micron. So that emissive power, or that power which is generated within the 0.4 to 0.7 because of 0.4 to 0.76 micron of wavelength is known as the spectral black body emissive power. So here as written, amount of radiation energy emitted by black body at an absolute temperature T per unit time, per unit surface area, and per unit wavelength about the wavelength lambda. For example, we have just discussed, we are more interested in the amount of radiation and light bulb emits in the visible wavelength spectrum than we are in the total amount of emitted, total amount of electromagnetic wave emitted. So that equation, the relation for the spectral body emissive power, EB lambda means emissive power of particular wavelength lambda is developed by Max Planck in 1901 in conjunction with the famous quantum theory. This relation is known as the Planck's law. It is expressed as Eb lambda at particular temperature. This lambda comma t represents wavelength at particular this temperature is equal to C1 divided by lambda raised to 5 in bracket exponential of C2 divided by lambda t minus 1. Here C1 and C2 is the constant whose values are as per this C1 is equal to 3.742 into 10 raised to 8 watt. C2 is equal to 1.439 into 10 raised to 4 micron. Here in this equation T is the absolute temperature of the surface, lambda is the wavelength of the radiation emitted, and K is 1.3 into 10 raised to minus 23, which is known as the Boltzmann constant. This relation is valid for a surface in a vacuum or gas. Now another law which is related to radiation is Wien's displacement law. It suggests that in 1893 Wien displacement established a relation between the temperature of a black body and the wavelength at which maximum value of monochromatic emissive power occurs. According to Wien's law, every body at a particular temperature have a maximum wavelength for the emission. So it states that the product of lambda maximum, it means maximum wavelength at particular temperature T. So product of this lambda max into T is always constant. We can find out value of this lambda max into T by differentiating Planck's equation. So here we have written equation which is given by Planck for the monochromatic emissive power. So to find out value of this lambda max into T, we have to differentiate this equation with respect to wavelength. It means by the lambda. So d by d lambda of this equation, emissive power of monochromatic emissive power at particular wavelength. So let's differentiate this equation with respect to lambda. So we will get by differentiation of this equation, in a numerator we have C1 lambda raised to minus 5, in denominator we have exponential of C2 by lambda t minus 1. So differentiation of this equation would be, first we will put this denominator as it is, and differentiation of this numerator, it will C1 into lambda raised to minus 5, it will give minus 5 into C1 to lambda raised to minus 6, denominator as it is, minus differentiation of denominator, putting numerator as it is, C1 lambda raised to minus 5 as it is, differentiation of this exponential C2 by lambda t minus 1. So e raised to something will remain as e raised to something as it is. Differentiation of C2 by lambda t will become C2 by t. C2 by t constant, 1 minus lambda becomes minus 1 upon lambda square, and in upon square of the denominator, which is exponential of C2 by lambda t minus 1 square, is equal to 0. Now if we cross multiply this exponential term with 0, it will become 0. Simplifying this equation, we will get this equation. Now here we can see that here this is a minus 5 C1 lambda raised to minus 6, minus 5 C1 lambda raised to minus 6, and here C1 lambda raised to minus 5, and 1 upon lambda from this equation gives us a lambda raised to again minus 1, so it becomes lambda raised to minus 6. So simplifying this equation, we will get minus exponential of C2 by lambda t plus 1 upon 5 C2 1 upon lambda t, exponential of C2 by lambda t is equal to 0. By trial and error method, solving this equation, we will get C2 by lambda max t is equal to 4.965. Now putting the value of C2 in this equation, we will get the relation lambda max into T is equal to 2898 micron Kelvin. So this is the final equation, final value for the Wien's displacement law, which is calculated by the differentiation of Planck's equation, which is lambda max into T is equal to 2898 micron into Kelvin. Now let's discuss some surface emission properties. The rate of emission of radiation by black body depends upon the following factor, as we have just discussed: temperature of the surface, nature of the surface, and the wavelength or frequency of the radiation. So parameter which deals with the surface emission properties, first is a total emissive power, Total emissive power, it means the amount of radiation, total amount of radiation which is emitted by the black body per unit area in time, watt per meter square. It is known as the total emissive power. It represents the whole emissive power by all the range of wavelength of electromagnetic wave which is emitted by any body. It is known as the total emissive power. And for the black body emissive power, we know the equation which is given by Stefan-Boltzmann is EB is equal to sigma T raised to 4. Here sigma is Stefan-Boltzmann constant, whose value is 5.67 into 10 raised to minus 8. Now second is a emission from the real surface. This equation is valid for the black body. Now for the real surface, the equation will become capital E is equal to, this is emissivity of a real surface. This epsilon is emissivity of the real surface into sigma into area. This is the area, real area of the body, and this is the temperature raised to 4, temperature of the body. Here this is the emissivity. It is the ability of surface of the body to radiate or to emit the electromagnetic wave or to emit the heat. Ratio of emissive power of any body to the emissive power of the black body, because we know that this sigma into area into T raised to 4 is our black body emission. So E by EB is known as the emissivity of any body. It is the ratio of emissive power of any body to the emissive power of the black body. It is known as the emissivity of any material. Now, as we know that electromagnetic wave is responsible for the radiation mode of heat transfer. So it is wave. So when one electromagnetic wave which is emitted from the body 1 and it incident on another body, another surface of the body 2, there are some wave properties like absorptivity, reflectivity and transmittivity. So let's discuss that. Suppose in this figure we can say that there is an incident radiation, capital G. It will incident in this surface. Now there will be 3 phenomena which will occur for this incident radiation, for this incident electromagnetic wave. Some portion of this wave will reflect, some portion of this wave will transmitted through this body, and some portion of this wave may be absorbed by the body. So the total amount of wave which is incident on this body is capital G. Now from this capital G, some portion will reflected, which is denoted by G suffix in suffix R. Some portion will absorb, so capital G in suffix A, and some portion will transmitted through the surface, through the material, so capital G in suffix small t. Total amount of G, which is divided in 3 parts, some will absorb, some will reflect and some will transmit. So dividing this equation with capital G in both sides, we will get this equation. In this equation, this GA by total G, amount of electromagnetic wave is absorbed divided by total amount of incident, is known as the alpha, which is absorptivity. This GR by G, amount of radiation which reflected divided by total amount of radiation, is known as the rho, which is reflectivity. GT by G, this is the amount of radiation which is transmitted divided by total radiation, is known as the transmittivity, denoted by tau, and this G by G is equal to 1. So for any body, alpha plus rho plus tau, absorptivity plus reflectivity plus transmittivity is equal to 1. Okay. Now in this equation, for a black body neither reflects nor transmit. It will absorb all the radiation which is incident on it. So for the black body, alpha is equal to 1 because it absorbs all the radiation. It will not reflect any radiation. It will not transmit any radiation. So for black body, alpha is equal to 1 because rho and tau is 0. For opaque body, no incident radiation is transmitted. So for opaque body, tau is equal to 0. So from this equation, alpha plus rho is equal to 1. For a white body will reflect all the radiation falling on the body. So for white body, alpha is equal to 0. There is no absorption. There is no transmittivity. So tau is equal to 0. So for white body, rho is equal to 1. Reflectivity is equal to 1. For a gray body, now if the radiative properties alpha, rho and tau of a body assumed to be uniform over the entire wavelength spectrum, then such body is known as the gray body. Again I repeat, what is gray body? a body which have radiative properties alpha, rho and tau assumed to be uniform over the entire wavelength spectrum, then that body is known as the gray body. Now there are two kind of reflections. One is a regular reflection, as we can understand from this figure. The angle which is made by the incident radiation with this reference line and the reflector radiation is the same, then it is known as the regular reflection. And second one is a diffuse reflection. Here from figure you can understand what is diffuse reflection. The angle which is made by incident radiation and the angle which is made by reflected electromagnetic wave is differ. So that is known as the diffuse reflection in on direction. Now one more important law is a Kirchhoff law. Here from the figure you can see that there is a one small body whose surface area is As, whose emissivity is epsilon, whose absorptivity is alpha. It is enclosed by one another body whose temperature is capital T, which is isolated from the surrounding. Now, radiation incident on any part of the surface of small body is equal to the radiation emitted by a black body at temperature T. This black body, whose temperature is T, whatever amount of electromagnetic wave is emitted from this black body will going to incident on this small body whose surface area is As. Okay, and that amount is going to be sigma into T raised to 4. From the Stefan-Boltzmann law, we know that the emissive power of black body, which can be calculated by sigma into T raised to 4. This all radiation will absorb by this small body per unit area, per unit of its surface area. So the amount of electromagnetic wave which is coming from this black body to this small surface area As, to this body, the amount of that electromagnetic wave which is going to be absorbed by this body will be alpha into sigma into T raised to 4. Alpha is ability of this small body to absorb the electromagnetic wave which is coming from the surrounding, which is coming from this black body. Now there are some radiation which is emitted by this small body because its temperature is also above absolute zero. So amount of electromagnetic wave, or we can say that amount of radiation which is emitted by this small body is its emissivity into sigma into T raised to 4. For black body is sigma into T raised to 4. For real bodies it is epsilon emissivity into sigma into T raised to 4. So now we know that whatever electromagnetic wave emitted by this body will be absorbed by this black body. So considering that small body is the thermal equilibrium with the enclosure, we know that both temperature of both this body and the black body is T. So these both bodies are in a thermal equilibrium. So for thermal equilibrium, the net heat transfer between these two bodies should be 0. So whatever radiation emitted by the body must be equal to radiation absorbed by the body. Whatever, I repeat once again, for thermal equilibrium, because this black body is at temperature T, this is our body which is at also temperature T. So this black body and this real body both are at temperature T, which is in thermal equilibrium. So the net heat transfer between these two should be 0. So whatever amount of electromagnetic wave, or we can say that whatever amount of radiation absorbed by this body because of radiation of this black body equal to radiation emitted by this body. So we can write down epsilon into sigma into T raised to 4, which represent the amount of radiation emitted by this small body, is equal to alpha into sigma into T raised to 4, which is absorbed or radiation absorbed by this body from the black body. So from this equation, sigma into T raised to 4, sigma into T raised to 4 would be cancelled out. So remaining would be absorptivity, emissivity is equal to absorptivity. So whenever two bodies which are in thermal equilibrium, at that time emissivity of body is equal to absorptivity. See, it simply means the body who is in thermal equilibrium with the surrounding, at that time the amount of electromagnetic wave which is emitted by the body is the same as the amount of electromagnetic wave which is incident on the body, or which you can say that which is absorbed by the body, so that the temperature of that body with the surrounding will remain in a thermal equilibrium. and this law is known as the Kirchhoff's law, which is developed in 1860. Now, one another law is Lambert cosine law. It is a simple law. Emissive power in from radiating plane surface in any direction is directly proportional to the cosine angle of emission. Generally, a body whose temperature is above absolute zero temperature emits electromagnetic wave in all the directions. But the intensity of electromagnetic wave in a normal direction is highest as compared to other direction. So, if from this figure we can see that if we consider electromagnetic wave emission from this point, the intensity is in normal direction is the highest intensity, which is denoted by the IN. Now, if we want to find out the intensity of radiation from this point at particular this point, it means from angle, normal angle is theta. So from this point at theta angle, the intensity would be IN cos theta, which is denoted by I theta. The intensity of radiation from this point for the theta angle would be written as IN cos theta. This law is known as the Lambert cosine law. So that's it for today's lecture, today's session. In this session, we have learned about the black body radiation. Why we have studied black body? Because for the reference point, we need one standard body to which other radiative properties of real surfaces can be compared. And we also learned that all the bodies whose temperature is above absolute zero emit electromagnetic wave, and that electromagnetic wave contains energy. Now, amount of electromagnetic wave or the wavelength of electromagnetic wave, it depends on the different emission properties like surface material of the surface conditions, as well as the temperature of the surface. Now, black body is a perfect emitter as well as perfect absorber. It emits all maximum amount of electromagnetic wave at particular temperature. It absorbs all the electromagnetic wave coming from the surroundings. We have also learned different kind of law like Stefan-Boltzmann law, which gives us equation for the black body emissive power, which is sigma into T raised to 4. And then we have studied Planck's law, which give equation for the spectral emissive power. If we want to find out emissive power of particular wavelength, then it can be calculated from the Planck's law. If we differentiate Planck's law, we will get equation for the WIEN'S displacement law, which shows that at particular temperature there is a electromagnetic wave of a particular wavelength which is maximum as compared to other wavelength of electromagnetic wave, and the byproduct of that lambda max into T, combination of temperature and maximum wavelength at that temperature, it will give us constant, which is 2898 micron Kelvin. At last, we have learned Kirchhoff's law, which shows that at a thermal equilibrium condition, whatever the amount of electromagnetic wave emitted by a particular body, same amount of energy will be absorbed by the body from the surrounding electromagnetic wave. So for equilibrium condition, absorptivity is equal to emissivity. That's why our body will remain at the same temperature in thermal equilibrium with surrounding. At last, we have learned Lambert cosine law, which shows the intensity of electromagnetic wave at a particular direction. We know that for the real surface, the intensity of electromagnetic wave in a normal direction is maximum. So for other than normal direction, we just need to multiply by cosine angle. For angle theta, the intensity of radiation would be IN cos theta. So that's it for today's lecture. Thank you so much.